Here's a Sculk sensor, the project that honestly broke me. I don't know whether it's the module or me or maybe a combination of both, but this honestly takes a lot of calibration. I've been putting off this project, coming back to it, and even to the point where I was still trying to get it to work just a few days before filming this. And one of my biggest problems is that I just overthink things and try and overcomplicate something that could just be so simple. But anyway, it is to a point where it does work. It can detect the sound and it does do kind of a good job. Honestly, right now it's set really low, so if it picks up any noise, and it will activate. So I don't have the full output, but you can tell just based on how intense the light is, whether or not it is a full signal or not. In the intro, I'm using small speakers, so that means that it's calibrated so that I can pick up the noise. Me talking is a lot louder than just these speakers, and so that's why if I even talk a little bit quiet, and it still picks up a loud signal. But anyway, let's see what's on the inside. For the construction itself, it is three parts. There's a base, the body, and these fins. The fins are printed flat and then they're bent so that they can be poked through the body. And what you're left with are these little tentacles. I was able to fit everything into the Sculk sensor and could even add a battery. I have it separated into two parts, the microcontroller side and the microphone module side. In the body, I have two pairs of LEDs that get a signal from the microcontroller to turn on. Then after 1.5 seconds, they turn off. The module I'm using is a Max4466. In order to get the module to pick up the sound I want, I have it set pretty low on the gain. And on top of that, I have a stepwise function for the redstone output. The reason why this project is so heavy is because loudness is not something that's linear. And so you have to accommodate that by fixing it. But even then, loudness is also just relative. So something quiet can have levels of quietness, and something really loud can also have levels of being loud. So instead of going through all the mess, I decided to just pick one gain setting and accommodate for a speaker. For the microcontroller, I'm using the Atmega 328P. It's just a condensed version of the Arduino Uno. I have a speaker that makes a clacking sound. I could try and recreate the tone, but I think I like the clacking a little bit better. I have it as a simple pattern, but you could just randomize it and have a more different sound. I have a capacitor hooked up to the power supply, and this really helps with lowering the noise. In the beginning, I had a really bad issue where there would be these spikes, and the spikes wouldn't dissipate. And I would notice that the spikes come from when I put a delay in the microcontroller. The capacitor didn't get rid of these spikes completely, but it does help dissipate them and limit them. Because of these spikes, I would get caught in a loop, and so it would just keep activating again and again, and it wouldn't dissipate the spike. So in order to accommodate that, I wrote some extra lines of code in order to detect these spikes and ignore them completely. And after that, it's a lot more reliable and only detects the sound. The noise level is dependent on the sensor itself, so if you have a high gain, then there's going to be a lot of noise. So you have to change this reference. So I have sensitivity and I also have a buffer. The buffer is there to ignore any noise in the circuit. The sensor sends out a voltage that is between 0 and the voltage supplied. In the code, this is between 0 and 1023. Microphones are just more sensitive speakers, so when you hit the diaphragm with sound waves, that generates a voltage. The voltage is amplified and then sent out. In the resting state, it's normalized to half of the input voltage. This is because sound waves are oscillations. I set the thresholds in order to determine what loudness will send out which signal. The microcontroller constantly checks the voltages, and if the voltage is higher than the buffer, then it will go ahead and collect a lot of voltages and determine what the peak is. It'll send a redstone signal based on that maximum. Something to keep in mind is that when you're using a serial monitor, it does slow down the microcontroller. So when I stopped the serial monitor and transferred it into the Sculk sensor, it did seem like it was detecting way too quick. How I have it set up right now, it's detecting a lot quicker and collecting a lot more samples. One example is that when I speak, you can see it activates right away. There's a slight delay to it, and it's because it's trying to detect any peaks when it detects something above the buffer. If you're using something that has a button, when you press down, it could just detect that button. You can see this effect because if I slowly press it, design could be improved by having microphones on each side since the Sculk sensor is directional. And that would also allow a lot more data to be collected instead of just having one point of reference. In order to connect the parts, I try out this 4-pin method, and it is a little sketchy because some of them are really close to connecting and shorting out. I did this to test it out, but also there wasn't enough room to fit the module in here. Realistically, I could have just shrunk this down and made everything fit better. That's pretty much it. Let me know if you have any questions, and thank you for watching.